All right, so for today we want to look at trigonometric integrals. And trigonometric integrals are, or let's say trig integrals, are integrals involving powers of trig functions or products of powers, okay? So powers or products of powers of trig functions. Okay, so in general, the vast majority of the time, our approach to these problems is going to be with the intention to do a U sub. I mean, we're always first fallback is U sub anyway. If we can do a U sub, great. But if a straight U sub doesn't work, we're still ultimately trying to work it so that we can get it to be a U sub. Okay, that's usually gonna work, vast majority of the time with very few exceptions. So we're looking, our strategy is U sub. Vast majority of the time, okay? And what we're gonna do in order to make that U sub work is we'll hold off, we'll save for later, du, and then convert the rest. Convert the rest. Hold off du, convert the rest. That's the biggest strategy. Most of the time, that's going to work. The rare exceptions where it doesn't work, usually we're stuck with only even powers, particularly like even powers of sine. In which case, let's see, like if we have only even powers, these, let's say if not, so if our U sub doesn't work, generally we're going to resort to power reduction. Okay, so reaching back, I mean the trig rule, power reduction rule for trig functions, or possibly just go back to the basic definitions, like, you know, the cotangent is the cosine over the sine, and those sorts of basic definitions of functions, and see if anything will simplify. So definitions is another strategy. Okay, so that's generally, the power reduction is going to come if we get stuck with even powers, particularly with sine and cosine. And otherwise, if we have something, we try to do our U subs, we try to see if we can hold off and convert anything, and it doesn't work, it might help us just to go back and convert stuff by definition. The other main exception, the weird one, is odd powers of secant. So odd powers of secant. We saw in the last video when we did biparts, that's odd powers of secant, we can do those by parts. We resort to biparts. Okay, but that's only, like I say, for odd powers of secant, and it's all odd powers of secant. We have to do biparts repeatedly and that sort of thing. Okay. So that's our general strategy. Hold off du, convert the rest. If that's not going to work, maybe I can bring some trig rules, power reduction to those. Or maybe it's an odd power of secant, I need to do biparts, or just resort to definitions and see if I can simplify things. Okay, just to remind you guys, the power reduction, at least for sine square of theta, is 1 minus the cosine of 2 theta over 2. So the sine one is the negative. Cosine square theta is 1 plus cosine of 2 theta over 2. And then the tan squared is just the sine squared over the cosine squared. So, okay. So those are the power reduction formulas that we'll resort to. Like if I have just an even power of sine, actually we'll do that shortly. But if I just have an even power of sine, then I'm going to reduce the power and go from there. Okay. Just to remind, other useful tools or things that we'll be using often for these, things like, well, the derivative of the sine, I'm switching between x's and theta, sorry, but the derivative with respect to x of sine is cosine. The derivative of the cosine is negative sine. Derivative of the tangent of x is the secant square. The derivative of the secant is the secant tangent. And then, of course, the cos are just the negatives of those, right? The derivative of the cotangent is negative cosecant square, and the derivative of cosecant is negative cosecant cotangent. Okay, so those are the primary ones that we'll be using. We got to keep those kind of in the back of our mind, those derivatives, in order to hold off our du's, okay, in order to know what to hold off for later. Okay, so that's just a reminder of some of the basic rules that are hanging around in the background that we might need to rely on. Power reduction and some of our basic derivative stuff. Okay, so let's look at some examples. Let's start with integral of cosine to the fifth sine dx. Now, just because you have a hammer doesn't necessarily mean that every problem's a nail. So I may or may not want to hold off a du for this, but let's see. Can I just straight u sub? Right? Well, let's see. If u is cosine, then du is negative sine x. The negative doesn't bother me, right? I can just pull that outside. And I've got the sine x sitting right there already. Okay, so there's no extra work that needs to be done here. This is just straight u sub. Negative u to the fifth du, right? My negative came out here, and I just pulled it outside. Oops, I forgot my dx. Sine of x dx, that was the negative du. And then I just have u to the fifth. So this is power rule, negative u to the sixth, add 1, divide by the new power. Back sub my u, negative cosine to the sixth of x over 6 plus some constant. Okay, so in this case, we didn't have to do any extra work. If u sub is going to straight work, then run with it, right? That's easy peasy. Okay, we could have actually made it hard, and we could have said, well, I'm going to u sub for this sine, which means I need the derivative of cosine. I hold that off, and I'll have cosine to the fourth that I'll need to convert. We could have done it that way, and it would have worked. But if I can just u sub, of course, that's going to be my first strategy. Okay. So let's say instead that we had, let's say, cosine cube, sine cube, something like this. Now, if I want to u sub for the cosine, my derivative is going to be the negative sine, but I've got sine cube in there. I've got more than just sine. So a straight u sub there wouldn't work. What if I tried to go the other way? If u is sine, the derivative would be cosine, but I've got cosine cube. Again, I'm stuck there. Okay, so now this is an interesting type of question, because we can do it both ways. We can do it either way. My strategy, again, is to hold off du and convert everything else. Now, the conversions that we're going to use are our Pythagorean identities, right? Cosine square plus sine square equals 1. Divide by the cosine, we've got 1 plus sine over cosine is tan square. 1 over the cosine is the secant square. And instead divide by sine, we get the cotangent square plus 1 is equal to 1 over the sine, so the cosecant square. Okay, so those are our three Pythagorean identities, and those will be what we use to convert back and forth. If I wanted to go between sines and cosines, I can use this one. If I want to go between tangents and secants, I can use this one, cotangents and cosecants, that one. Okay, and I can convert them back and forth. So let's see, I want to do it both ways. So I want to go, if u is the cosine, let's say, cosine of x, that will mean that du, the derivative of the cosine is negative sine of x, dx. Negative doesn't bother me. So I need a sine x for my du, right? I need this sine x for du. So I'm going to take one of these sines and hold it off for du. So I'm doing this. Cosine cube of x. Now, whatever that power is doesn't bother me, because I'm going to u sub for it regardless. And that'll just be a straight power rule. Doesn't matter what that power was. Okay? But here I've got sine square of x, sine of x, dx. So I've pulled one of those sines out of that sine cube, holding this off for my du. The rest here I want to convert. I've got an even power of sine, so I can use Pythagorean identities to convert the rest of this to cosines. All right, so I'm going to leave that sit there. I'm holding that off for later. And this, I'm going to use my Pythagorean identity to convert. So we've got cosine cube of x. Here, this is 1 minus the cosine squared of x, sine of x dx. Now we can just distribute, and when we, in this next step, you'll see that, it'll be a straight u sub, because our du is going to be sitting there. It's nice. So cosine cube sine x dx, cosine cube sine x dx. Okay, that was this first one. And then minus, we've got cosine to the 5th sine x dx. And they are beautiful. Here our du is just sitting there, right? If we want to u sub for our cosine, du is just sitting there. Fantastic. So we do need to worry about negative signs, right? Because the sine of x is negative du. So here I have negative integral u cube du plus integral u to the 5th du gives me negative u to the 4th over 4 plus u to the 6th over 6. And all we need to do now is back sub. I don't want to go off the screen, so let's see. We have my u was cosine, so we have cosine to the 6th x over 6 minus cosine to the 4th over 4 plus c. Noise. Okay. Cosine to the 6 over 6 minus cosine to the 4th over 4 plus c. Sweet. Now, let me hold that off up here for a moment. We've got cosine to the 6th over 6 minus cosine to the 4th over 4 plus c, just to allow us some space rather than squinching in over here, right? And we'll say, okay, let's see what happens if we decided differently. Would it have worked? Okay. So last time we took the route of u equal cosine, and so du was our negative sign. Let's say we instead chose to make u equal to the sine of x, in which case the derivative of sine is cosine of x dx. Okay. So that means I want to hold off one of the cosines for du for later. I have a cosine square of x, sine cube of x. Again, I don't care what power that is because I'm just going to u sub for it and it'll just be a power rule. But I'm holding one of those cosines off for later for du, cosine x dx. Now the rest of these cosines I want to convert just to sines. So I have an even power of cosine, that's going to work. I can just convert using 1 minus the sine square. Sine cube cosine x dx. Okay, and I'm just distributing through now. We've got sine cube of x cosine x dx minus, this will give us a sine to the 5th, sine to the 5th cosine x dx. And beautiful, right? Here our du is just sitting there waiting for us to u sub. In this case, I don't have to worry about the signs all flippy-flopping because it's just a positive. So we have u cube du minus u to the 6th, oops, integral u to the 5th du so it looks like u to the 4th over 4 minus u to the 6th over 6. Our u this time was the sine. So back subbing, we've got sine to the 4th over 4 minus sine to the 6th over 6 plus c, and we're done. Sine to the 4th over 4 minus sine to the 6th over 6 plus c. Now, what that means, we've done the integral, the same integral, twice. Right? We've just done it two different ways. So that has to mean that if we haven't made an algebra error somewhere, that these two are exactly equivalent to each other. They're algebraic manipulations of one another. I'll leave it to you as an exercise to prove that that's the case. Right? We have sine squared squared and then sine squared cube, and we just have to distribute all that out and combine our like terms and see what we get. But there's often more than one way to skin a cat is one of the lessons here, right? We can approach a problem multiple different ways depending on if it'll actually work. We can get different looking answers, but they're actually not different. They're equivalent. They're algebraic manipulations of each other. Sweet. So that gave us an example of doing the sine or cosine substitution either way. In fact, spoiler, I'll try to include the proof that those two are equivalent in the comments below. We'll see. Okay. Good deal. Let's try, how about secant to the fifth tan cube of x dx. Excuse me. Secant to the fifth tan cube. Okay. So, again, my primary strategy is going to be to try to u sub. If I want to u sub for secant, I'm going to hold a secant tangent off. Would that actually work? Let's see. That would leave me a secant to the fourth of x tangent squared of x secant of x tan of x, tan of x dx. So my goal here, I didn't think this would actually work. Let's see. If u is the secant of x, then du is secant tangent dx. So I was holding off that, pulling one power of secant and one power of tangent out and seeing what's left. Well, it doesn't bother me what power that is because I just want to u sub for it. Here I've got an even power of tangent. I think I can convert that to secants. Sweet. So I've got secant to the fourth times tan square is secant square minus 1. Subtract my 1 over, right? So secant squared minus 1. Converting that, and I've got a secant tangent that I'm just chilling on for later. Secant x tan x dx. That's my du I'm holding off. And this is looking good. Let's see, we've got secant to the sixth. Secant to the sixth, then secant tangent. Dx. Cool. Minus, let's see, it's just a secant to the fourth. And then the secant tangent dx. And there my du is appearing in both of those. So I can just straight u sub for secant. Those will be power rules. Integral u to the sixth du, right? Du is secant tangent dx. Minus integral secant to the fourth, so u to the fourth du. Those are power rules. U to the seventh over 7, add 1, minus u to the fifth over 5. Now all we need to do is back sub for our u, secant. Secant to the seventh of x over 7 minus secant to the fifth of x over 5 plus c. Fantastic. Now, let's see if it would have worked if we try the other way. If I wanted to try to u sub for tangent, then I need du is the secant squared. So I'd need to pull a squared power of secant out of there. which would give me secant cube of x, tan cube of x. I pulled the secant square out of there to sub for tan dx. But now I have this odd power of secant there, so I'm stuck with that, right? I need an even power of secant in order to be able to do this conversion. I'd like to convert all those secants back to tangents so that I can u sub for them, but that odd says, nope, you're stuck right here. No, that's not going to work, right? So I could have tried it this way, but it wouldn't have worked. So I try to u sub the other way, pull my du out, hold it off for later, convert everything else, and it worked just fine. Then we just get power rules down here usually. Cool. So we've seen two examples with sines and cosines. We've seen secant and a tangent. We saw odd power of secant when we did by parts. Let's try one of the weirder ones, or one of the degenerate ones, right? That doesn't really fit. So let's say we've got just straight like sine square of x dx. Yeah? So I'm stuck only with an even power of sine here. I go, well, the only thing I can do is say sine square is 1 minus cosine square. But now I've got to integrate cosine square. Then the only thing that I would be able to do would be to say that it's 1 minus sine square, the cosine square, and we just zero out. We've just gone around in a circle and done nothing, right? So at that point, I'm really stuck. There's no way I'm going to be able to u sub anything. So this is when I'm going to resort to that power reduction formula. So 1 minus the cosine of 2x over 2 dx, right? Now, if it was sine to the fourth, then I'd have sine squared squared, and I just have this object squared up. I just have to distribute stuff out and split it. So it's the same strategy. We just have more algebra to do if it's higher even powers. Okay, but now here we can split. Now this is a first order. So this will be a nice u sub, right? I don't mind that there's a 2x in here. What I mind is that we have a composite on that sign. So here now we don't. And we've actually done something good. So we have 1/2 dx minus 1/2 integral cosine of 2x dx. And again, like I was saying here, we don't mind that that's, u is 2x, so du is 2 dx. I'm going to pull another half out, but that doesn't bother me. Otherwise, du is dx, and we're good. So this is easy enough to do. I can just, the integral of dx is x, minus, this is 1/2 integral. We have the cosine of u du, but I need to pull that other half out. Cosine of u du. So 1/2 x minus 1/4. The integral of cosine is sine. Sine of u, I might as well save myself a line. U is just 2x. Plus c. And we're done. Okay, so that's one example of one of the ones where our u subbing, we're just gonna, or trying to convert things, it's never gonna work. We just go around in a circle. So we reach back to trig, power rule, or power reduction, and bam, off we go, easy. right. Let's try another weird one. One that's sort of an exception to the rule. How about 1 over secant of x tangent of x dx? Okay. So I look at this and I go, my best bet, my first best bet would be to u sub for the entire denominator, in which case it's just ln of whatever's under there and we're done. But then I'd have to have the derivative of secant times tangent, and we've got product rule, and I definitely don't have that. Okay, so the whole denominator, that's out. Let's see, if I could u sub for the tangent, the derivative of tangent would be secant squared. I don't have it, right? I have 1 over the secant. Crap, okay. If I wanted to u sub for the secant, I'd need the secant tangent. But if I'm u subbing for the secant, all I have left is the tangent downstairs. So again, no u subbing, nothing is going to work. Now, there's no rule for me to convert secant tangent, right? I'm really just stuck with that there. And I go, but wait a minute. Secant and tangent, they're like reciprocals and relationships of other basic trig functions, sines and cosines. So let's see if we can plug some stuff in there, simplify, and see if life gets any better. So this is where one of the ones where I'm going to resort to definitions. I say, okay, well, the secant is 1 over the cosine. Okay. The tangent is the sine over the cosine. Looks like I've got 1 over the sine of x over the cosine squared of x, which will flip over, and I've got cosine square of x over sine of x dx. Nice. Now, have I done anything good or not? Yes and no. In one sense, yes, I've made my life simpler. Instead of having to worry about reciprocals and tangents underneath and reciprocals of reciprocals, that's all taken care of. We've done it in the algebra, right? In the trig. Now I just have a relationship between our two basic functions, sine and cosine. So yeah, that's a simpler problem. It's easier. So I've made progress in that sense. But the question is, now what do I do? I've got a new problem that's equivalent. All I've done is just use the definitions. So these are the same problem, but now I got to attack this problem. And I'm going, okay, well, how do I do that? Well, I'd really like to u sub for sine, right? Because if I can u sub for sine, then it's just ln of sine and I'm done. The derivative of sine is cosine, and I've got a cosine, but then I have an extra one, right? I've got cosine squared upstairs. Crap. If I want to u sub for cosine, I'd need my sine upstairs, but it's downstairs. So I'm kind of stuck there. I can't just straight u sub it that way. I say, but I have an even power of cosine upstairs. I can convert this entire problem just into sines, and maybe other things will simplify even more. So that's good. I'll try that. And I'll say, well, cosine squared is 1 minus the sine square over the sine dx. And I say, I think I'm making progress now. We have integral of 1 over the sine, minus sine squared over sine is just the sine. So that one, this is just a basic rule, right? Integral of sine is negative cosine, so we can just complete that, and we're done. Negative, negative gives me positive, right? So sine of negative cosine. Now here, we've got a quotient business going on, but if we just revert back to the definition again and say, well, 1 over the sine is the cosecant, now we're back to a basic rule again. Integral of cosecant is what? Negative ln, absolute value, cosecant plus cotangent plus the cosine plus c, and we're done. Okay, so that one ended up reducing to a basic rule as well as this one. We just needed one more step there. Yeah. Nice. So that was another example of sort of a degenerate one where we try to go about doing a U sub and it doesn't quite work. We can't really convert anything either, so we fall back to the basic definitions, take another glance at the problem, see did we help ourselves, and yeah, we did. We made it doable, so that's good. All right. Good. How about integral sine cube of 4x dx? Sine cube 4x dx. Okay, so sort of my initial instinct, this thing's all sines, right? So if I could U sub for the sine, that would be fantastic. That's kind of my goal. But if I U sub for sine, then I'm going to need cosines in there. So let's see. I can convert a sine square. So let's split it. Let's say sine square of 4x sine of 4x dx. Those I can convert to get the cosines in there that I would have wanted. Integral 1 minus the cosine square of 4x sine of 4x dx. Now when I distribute, I've got integral of sine of 4x dx. That's okay. This is doable. It's just a straight U sub. Right? I need to U in there for the composite 4x, but I'm just going to get the quarter outside and no problem. Okay, so this is totally doable now. And we have minus the integral of cosine square of 4x sine of 4x dx. And I say, okay, how am I going to deal with that guy over here? My initial instinct was trying to U sub for sine, because that's really all I had. But I had to get some cosines involved in order to do that anyway. So I got the cosines involved, I converted off what I could, and now I've got this cosine squared. Well, if I go 1 minus sine squared again, I've gone around in a circle. I haven't done anything good. But, see, what's the derivative of the cosine? It's the negative sine. So originally I thought that I was going to U sub for sine, but it looks like if I U sub for cosine of 4x, what's du? Well, it's chain rule. So the derivative of cosine is negative sine of 4x times the derivative of the inside, chain rule. So there's a 4 dx. And look at that, I've got the sine 4x dx sitting right there. The negative 1/4 that'll come out here doesn't bother me, right? Sweet. So this one's, well, let's just say if we're going to use a u over there, no, it's a different u, so it's fine. U equal 4x here means that du is 4 dx, means that quarter is going to come outside. So I've got 1/4 integral sine of u du. Over here, I have the negative negative, so that'll become a plus. The 4 comes outside. Integral, excuse me, the cosine of 4x is my u, so I just have u squared du. So that's power rule. Nice. So integral of sine negative cosine, it'll be negative cosine of u, and let's just back sub our u here to save us a line, 4x. And here we've got power rule, so it'll be 4u cubed over 3. And our u cubed, let's just save ourselves a line. U in this case is cosine of 4x. So cosine cubed of 4x. Back sub in that u on that piece. There's the u cubed over 3 plus c, and we're done. So even though we originally thought we were going to u sub for sine, so we needed to get some cosines in there and convert, we ended up u subbing for cosine. That's fine. It's okay. The same intuition, the same goal, trying to hold off a u, or the du, and u sub, led us in this path anyway. The same sort of thinking. Cool. Let's see. We've done odd powers of secant tangent business. We did combo of odd power of cosine and sine. We did even power, use a power reduction, even power of sine. How about tangent to the fourth? Integral tangent to the fourth dx. Okay. Here again, we're stuck with only even powers, but we're still on that track to see if it'll work, to see if we can hold off du and sub. So I'm on the road of trying to u sub for tan. If I could u sub for tan, this would just be a power rule. But du is secant square, so I need to get some secants involved here. And say, do I have enough to get secants in here? Well, I need a tan square, right, in order to convert. So I say, yep, I can split this as a tan square by pulling one tan square out. Great. So I pulled one of the tan squares out, and I've got a tan square here that I want to convert in order to get those secant squareds involved, so that I can try to do a u sub. Tan square is secant squared minus 1. Secant squared minus 1 dx times, we've got that tan square dx. Sweet. So let's see what we get. We're going to split those. Secant square x tan square x dx. and minus integral tan square x dx. Now let's see. Our original idea was to u sub for tangent, so let's see if that'll still work. That's hopefully what we were trying to do. That's why we got that secant squared involved, right? Well, yeah, if I u sub for tan here, if u is tangent, then du is secant squared dx, which I've got sitting right there. Beautiful. So this is a straight u sub, u squared du, right, which gives me a u cubed over 3, but in this case our u is tangent, so tangent cube x over 3. Okay, so we got this piece done in the way that we were hoping. We wanted to u sub for tan, and so we got the secant involved. There our du is just sitting right there. Beautiful. Now, this tan square. We can, if we were trying to u sub for tan, we need a secant squared in there. But wait, secant squared is one of our basic rules, right? It's easy to integrate. We know that the integral of secant squared is tangent. So it looks like if I can just convert that back, I'll get a secant squared sitting in there that I have to integrate, but that's easy. Okay, so I've got minus integral, what's the tan square? Secant squared minus 1. Which means I have minus integral of secant square x dx, that's what I was anticipating, right? That's easy to integrate. That's just the tangent. Plus, and then I've just got the integral dx. So that's also super easy. Integral dx is just x. So we have minus tangent of x plus x plus c, and we're done. All right. Okay, so that was even power of tangent. We were just still on the same road, trying to u sub and convert everything, hold off u and convert everything else, or convert what we can to try to do it. Let's try a similar one, but it plays out slightly different. Because this one ended up being easy, right? Or not being easy. We had this tan square that we had to convert back again, and then it was easy. Let's say what would happen if this was a secant. So secant to the 4th. All right. Similarly, say, well, I'd like to u sub for secant, but then my derivative is secant tangent, so I need to get tangents involved here somehow. Seems the only thing I can do is pull a secant square out to convert, because I need a secant squared for my formula. So I've got one secant squared and then another one that I'm pulling out so I can convert this. All right, secant squared is 1 plus the tan square. Secant square dx. Okay. So on the first one, I'm going to get integral secant square x dx. But that's one of our basic rules, right? That was even easier than last time. Last time we had a tan square that we had to deal with and convert it back to secant squared. But here I've just got a secant squared. So that's tangent. And on the second one, we have plus integral. We have tan square secant square dx. Tan square secant square, x, dx. And I go, if I u sub for tangent here, even though my first instinct was to u sub for secant, but if I u sub for tangent here, then du is just sitting right there. Secant squared x dx. So that's easy. This is integral of u squared du, where u is the tangent, right? U is the tangent, so du is secant square x dx, which was just sitting right there beautifully for me. So that's a power rule, u cubed over 3. U cubed over 3. And my u in this case was the tangent. So I've got tangent cubed over 3. And let's just put that together. This is over here, right? So I have tangent of x plus, this was all plus, right? Plus c. So this tangent was from here. This tangent cube came from this piece, and then plus c at the end. Sweet. So again, holding that du off and trying to convert, or trying to convert so that you can u sub. These are, most of the time, they're going to work for you. Sometimes we'll be able to even approach a problem one way or the other, right? Let's say if I had something like, just as a quick example, let me see if I can make this something like sine to the 91 of x cosine to the 13th of x dx. Let's see, did I screw myself up by doing that? I think I screwed myself up. What the example I'm trying to do, or what I'm trying to say, is some of them will scream at you which one is obvious. In this case, no, by putting this here, it sort of screamed at me here. Let's make that a cubic, just to make it slightly more obvious. Okay. I could, just as looking at this, we're not going to do it. I mean, I suppose we could, but just to look at it, right? We could u sub for cosine, which would give us the derivative sine, which means I'm going to hold one of those signs off, and that'll give me a sine to the 90th power. Well, that'll be sine squared to the 45th power. The sine squareds I can then convert to cosines, but then I've got the 45th power that I have to distribute. Now, it'll work, but I don't want to do that algebra, right? Okay. On the other hand, this is sort of screaming like, if you u sub for sine, then it's just going to be u to the 91th power, and we don't care what power that is, right? Because it'll just be a power rule. What's at stake is, am I going to be able to hold a cosine off? Because if I'm u subbing for sine, I need a cosine, and then be able to convert everything else. I go, yeah. Now, in this one, it's like blaringly obvious that we want to do u equal to the sine of x so that I get a power rule on that. If I get sine, I'll get sine to the 91x. I need to hold one of the cosines off for my du, right? Which will leave me a cosine square here, which I can convert to sines. Once I convert to those signs, right, we're just distributing through, and we've got powers on sine. They're just u subs. So if you see a question that's like that, where like one of them is outrageously big and the other in comparison to the other one, that's almost always the one you want to sub for. If they're close together, like one is a 5 and one is a 3, then we can kind of, it's a wash. You can do it either way. One's going to have more algebra. You're just going to have to distribute more stuff out, but they'll be equivalent, right? They'll be algebraic manipulations of one another. Okay, I think we've seen examples of all the odds of sine and cosine. Odd powers of secant, that's a weird one, right? Those are biparts. If we get only even powers, if we're stuck with only even powers, particularly of sine and cosine, then we'll use power reduction rule. But otherwise, we're always just trying to hold that du off, convert everything else. Cool.